When dealing with the salt, previously we said a salt either dissolved in water or didn't dissolve in water. We're going to look in a little more detail at salts that we said did not dissolve in water, such as lead 2 fluoride. Here's the equilibrium reaction that would take place when lead 2 fluoride dissolves. It dissociates into the lead cation and 2 fluoride anions. What makes this a slightly soluble salt is the fact that this reaction has a very small equilibrium constant, meaning this reaction favors the reactant side. We can now calculate how many moles per liter of this solid would dissolve either in pure water or in a common ion such as a solution of sodium fluoride. Sodium fluoride is a completely soluble salt. Sodium fluoride dissociates into sodium plus and fluoride minus. So when we look at this ice chart for the reaction, KSPs always have the exact same form. They always have the solid on the reactant side, and they have the cations and anions on the product side. Solids, constant concentration, so we can exclude that column from our ice chart. The initial solution is 0.3 molar sodium fluoride. There's no lead cation from that solution, but there is 0.3 moles per liter of fluoride. So this reaction has to go to the right because we see the 0 in the ice chart. So the lead's going to increase, the fluoride increases. Lead increases by x and fluoride increases by 2x. So at equilibrium we get x and 0.3 plus 2x. We can take those values and plug them into the KSP. 3.3 times 10 to the negative 8 is equal to x to the first times 0.3 plus 2x to the second. Such a small equilibrium constant means that this x is going to be negligible, and so 2x is negligible compared to 0.3, and we can solve this by approximating 0.3 plus 2x squared as just 0.3 squared. So solving this equation for x gives you 3.67 times 10 to the negative 7th, and the approximation is valid when you check 2x divided by 0.3. This answer is less than 5%. Now the original question was how many moles per liter of this solid would dissolve in the water. Our answer for x, remember x came from an ice chart, and x has units of moles per liter. So this x represents the amount of lead cation that would dissolve in the water. But also notice the KSP always has a coefficient of 1 in front of the solid. This KSP reaction is always 1 mole of the solid turning into the cations and anions on the product side. So by stoichiometry, if the coefficient for lead is a 1, the lead fluoride is a 1, this x is also the amount of moles per liter of the original solid that would dissolve. This x is given a special term. It's called the molar solubility. So it really can be related to any of the three chemicals in this reaction. We can talk about how much solid dissolves. We can talk about how much lead cation we make. We could plug this x back in and figure out how much fluoride we have. We could also turn this into grams per liter. If we wanted to calculate how many grams per liter, we would just use our molar mass as a conversion factor to turn moles of lead 2 fluoride into grams.